Hello. Today we're covering interrupt service routines and real-time operating systems. So ISR stands for interrupt service routine. It's a physical action that will interrupt your loop. So in your Arduino, you have your setup and your loop. And in your loop, your Arduino it's just looping around doing whatever you're right there infinitely. So an interrupt will be a piece of code that will jump from your loop to there, and then the Arduino will take that whatever actions you have written in your interrupt, now it'll go back to your loop. This is used in every operating system, and in our case, following the simplicity philosophy that we have in this lab, we're gonna try to keep it simple and just only GPIO ISR, which is read ones and zeros. The best example that I have for an interrupt service routine, it's the mouse. Have you ever used your computer so much that it freezes? And then if you notice, nothing is running anymore. But the only thing that works, it's the mouse. When you move your keypad or your mouse around, even though your computer gets frozen, the mouse still works. And that's because it has an interrupt. So in our Arduino, which is the Uno one, we can only use two pins for interrupts, which is pin number 2 and pin number 3. The way to enable it, it's using the function that I have here written at the top. It's attach interrupt. Then we need to put digital pin to interrupt where we can write pin number 2 or number 3. After that, the second argument, it's going to be the GPIO ISR, which is the name of the interrupt. So that needs to match whatever interrupt you want to call later. And finally, we can have rising, falling, change, or low interrupts. So if you see the picture that I have here below, a rising interrupt, let's say you're using a push button, pull down, and you're not pressing the button, right? Then you press a button and you go to 1. So if you write rising in this function, in the moment that you press the button, you will go from 0 to 1. And at that moment, the interrupt will get activated. So your code is going to jump from the loop to this GPIO ISR function. Do whatever you have here and then go back to the loop. If you write falling, like in this example, if you press the button, it'll go up. So no interrupt will get activated. But when you release the button, which is when you go from 1 to 0, at that point, the interrupt will get activated because you're falling from 1 to 0. And if you type change, it won't matter if you go to 0 to 1 or from 1 to 0. As long as you change your level between 0 to 1 or 1 to 0, the interrupt will get activated and the code will jump from your loop to the GPIO ISR. And finally, we have low. So at any point where you're at low level, you'll jump to the interrupt to execute it. This is gonna make more sense once we go over lab example number 1, lab 7 example 1. Now for RTOS, that stands for real-time operating system. So an operating system, it's a software that controls computer hardware. You can see the sample picture that I have here on the left. The operating system, call it Windows, iOS, or whatever, it's a software that's controlling everything that the computer is doing. It has interface with the monitor, with the hard drive, with the mouse, printers, keyboards, and also all the applications that are running. So the operating system is the main software that creates the interaction between hardware and user. On real time, it's a specialized hardware that manages tasks with strict time constraints. That means that it's a software that, compared to a computer, let's say an operating system that you can use like Windows or Mac OS or Linux, in those cases, time is not really critical. So the operating system, let's say for instance, you're opening Word, working in Word while you're listening music, maybe running some YouTube videos or Spotify or whatever, you have a lot of applications running. It's not critical the amount of time that the operating system spends working in those. On the other hand, there are some devices where time it's something really important. Let's say an elevator. An elevator that's controlling going from floor one to floor two and floor three and floor four needs to have time constraints and be able to um, go to the floors in a time constraint. In the same way, the control panel for a plane and all the sensors are critical to have a real time responding. Think about it. What happens if one of those things get frozen? Those are risks that cannot be taken. So a real-time operating system, it's taking these two things together. It's administrating all the tasks that Arduino needs to do, but it also has a time constraint so that it's gonna finish whatever task it needs to do with time constraint. The library that we're gonna use is free RTOS, which you can find in your course. You can download it from Blackboard. Again, to try to keep things simple, we're just gonna create task using the X task create function. That one is gonna have 5 arguments, but we're gonna be end up using only 2. So alarm, in this case, that's the name of the task that I'm creating, and that name needs to match your task. This is gonna make sense once we go over lab 7 example 2 and lab 7 example 3. The task name can be whatever name you want to call it. We will use that. Stack size, just keep it at 128 to keep things simple. We're not gonna be dealing with parameters, so keep it null. Priority, it's gonna be 0, 1, 2, or 3. And the handle piles, just keep it as null. The priority, the lower the number, the higher the priority. That means that it's gonna be more important, or the task, it's gonna have more relevance. So priority 0 means like maximum priority. And priority 1 means that it has high priority, but it's lower priority than whatever task has priority 0. Your queues is what we're gonna use to send data between tasks. So if you have 3 tasks and you need to send data between them, we're gonna use queues. So you can think about it like a mailbox. A mailbox where you can put data and that data can be extracted from another task. And to control the resources between tasks, we're gonna use semaphores. An analogy that I have for that, it's you can see here how the traffic got jammed because all the 4 cars are trying to go through the intersection at the same time. So how can we control this with a traffic light? A traffic light, or well, yeah, 4 traffic lights, right? It's gonna stop the other 3 cars to move on the traffic line so that 1 car can cross per time. So that's how a semaphore works. It's gonna be a signal that's gonna be taken by one task so that the task can use any resource, any hardware resource. And once it releases the semaphore, another one can take it so that that one can use that task. You can think about it like the um, printers. When you try to print something uh, and you have one printer that's connected to a lot of computers, they need to take a queue or one space, and the semaphore it's controlling what print is going first. Because if everyone tried to use a printer at the same time, there's gonna be a mess. So with a semaphore, you can control what print it's taken by what computer. And that's all that we need to know about free RTOS and interrupt service routine. It's time to go over examples.